In this video, we look at a particle in a one-dimensional Leaky box. Such a box looks like this. It extends from 0 to A, and the potential energy function looks like this. It has an infinitely high potential barrier on the left. The potential energy is 0 within the box, and on the right there's a finite barrier of value V0. We have three regions: left L, center C, and right R. In order to get the wave functions for the energy eigenstates, we solve the Schrödinger equation for each of the three regions separately and then stitch the solutions together using boundary conditions. This is a general recipe for piecewise constant potential energy functions like this one. First, the left region. This is the easiest. Since the potential is infinitely high, there is zero probability of finding a particle there. The wave function is 0. Psi sub L of x equals 0. For the center region, the Schrödinger equation reads d squared dx squared of psi c of x equals negative 2me over h bar squared times psi c of x, which we can abbreviate as negative kc squared times psi c of x. Kc squared is the prefactor. We have seen this equation before. It has solutions that are linear combinations of a sine and a cosine function. Next, we impose the boundary condition that the wave function must be continuous at x equals 0. That means psi of c at 0 has to be equal to psi l at 0, which is 0. From this follows that psi c of x equals to a times the sine of kc x. In the right region, the Schrödinger equation reads d squared dx squared of psi r of x equals negative 2m times e minus v0 over h bar squared times psi r of x, which you can abbreviate with plus uppercase kr squared times psi r of x. Kr equals to the square root of 2m times v0 minus e divided by h bar. Now we need to make a distinction. If the energy E is larger than v0 or equal to v0, then the particle could escape from a box. Such particle states are called free states or scattering states. If the energy of the particle is smaller than v0, the particle is trapped. It cannot leave the box. Such states are called bound states. In chemistry, we are mostly concerned with bound states of electrons in atoms or molecules, so let's stick with bound states here as well. Note that for bound states, Kr is real. Therefore, a general solution of the Schrödinger equation is psi r of x equals some constant times e to the negative krx plus some other constant times e to the positive kr times x. You can easily check this by substitution. Let's look at the two terms. Clearly, these are real exponentials. The first exponential decreases rapidly with increasing x, so it's plausible for a wave function. The second exponential, on the other hand, increases rapidly with increasing x, so that it blows up. Such a function cannot be normalized and therefore cannot represent a physical state. We have to drop it and keep the decaying exponential only. Let's take stock. We have general expressions for the wave functions for all three regions: left, middle, and right. But we still have three unknowns. The energy E and the two scaling factors A and B from the wave functions. To move forward, let's apply the boundary conditions at x equals a. First, the wave function must be continuous at the boundary. Which means psi c of a has to be equal to psi r of a. This leads to a times the sine of kca equals to b times e to the negative kr a. Second, the first derivatives of the wave functions must be continuous at the boundary. This means that there shouldn't be a kink in the wave function. If there were a kink, the second derivative needed in a Schrödinger equation would not be defined. So the condition reads d psi c dx at position A equals d psi r dx at position A. And it results in a times kc times the cosine of kca equals negative b times kr times e to the negative kr a. Now we can divide the two equations. And we get 1 over kc times tangent of kca equals to negative 1 over uppercase kr. Inserting expressions from kc and from kr and moving the negative sign to the left-hand side, we finally get the tangent of the square root of 2me over h bar times a equals, with a negative in front, equals the square root of e divided by the square root of v0 minus e. The only unknown in this equation is the energy E, and we can obtain E from that. Unfortunately, this equation cannot be solved analytically for E. We need a computer to obtain the energies numerically. But we can clearly see that only certain discrete values of E are going to be allowed. The energy is quantized. To obtain the remaining unknowns, A and B, we need to go back and use the continuity equation from boundary condition number 1 plus the normalization condition. Again, getting A and B from these equations is only possible using numerical methods. In summary, we have looked at stationary bound states in the one-dimensional Leaky box and found that the energies are quantized.